Hello and welcome to this new video. In this video, we are going to finish section 1.3 by talking about periods of states in a Markov chain. So let S be the state of a homogeneous Markov chain, the state space of a homogeneous Markov chain. And for every state I in S, consider the set of integers, the positive integers, so starting from 1, such that PII to the n is positive. What does this mean? So n is in Ji if and only if there is a cycle or loop starting from I of length n. So I can go from I to itself in n steps. N is at least 1. So this is a set of positive integers. And we set di to be the greatest common divisor of Ji. Plus grand diviseur. It's possible that Ji is empty. I will give you an example right now. So in this case, we set if this is empty, it's convenient to set di equal plus infinity. Okay? Di is called the period of the state I. So what does it mean? So if n is in Ji and di is the greatest common divisor of Ji, then necessarily the di divides n. Therefore, if di does not divide n, then n is not in the set Ji. So this probability is the probability of PII to the n is 0. So there's no cycle of length n. And since it's the greatest common divisor, then di is the largest integer with this property. Okay. Now I will make things more clear on examples. When di is 1 or di is plus infinity, we say that state I is aperiodic. Now, when is Ji is empty? Ji is empty if and only if there's no cycle from I to I of any possible length. Which means that if I leave I will never go back. Okay? Even if I start from I. So here's an example. Consider this the homogeneous Markov chain on 3 states. So I suggest that you draw the transition graph of this Markov chain. But even if you don't draw the graph, you will see, since the first column is 0, this means that there is no path from state 1 or 2 to state 0. So if I am initially at state 0, then I can move either to state 1 or state 2, but I will never go back actually. Okay? So J0 is empty. Next example, very simple, a little bit artificial, but just to illustrate the set Ji. So first begin by drawing the transition graph of this Markov chain, which is a cycle. And now, what are the possible cycles from 0? The lengths of possible passes starting from 0. The shortest possible cycle is 0, 1, 2, 0. So it has length 3. But it's not the only one. There is a cycle 0, 1, 2, 0, 1, 2, 0. It has length 6, and so on. So actually, we see here that J0 is the set 3, 6, 9, etc. When we have a small graph or small Markov chain, we can analyze it graphically, which is very convenient. But when we have large graphs, we cannot analyze them graphically. And then we will need graph algorithms to tackle. So we need computer actually. Okay, and now of course by symmetry, so therefore actually what is D0? The greatest common divisor of the set is of course 3. So 0 has period 3. And by symmetry, okay, J1 is also J2 is the same set, and D1 equal D2 equal 3. Now, this is not a coincidence, because we shall see in a moment that all communicating states have the same period. Okay? Which is called the period of the class. Okay, last trivial example. Okay, here the situation is less symmetric. Okay. What is the smallest cycle starting from 0? From 0 I can go to 1, and from 1 I can go only to 2. Now from 2 I can go back to 1, but I could not go back to 0. So I have to go to 3 and then to 0. So the smallest cycle here is of length 4, 0, 1, 2, 3, 0. Now the next cycle has length 6, because for example you can take 0, 1, 2, 1, 2, 3, 0, length 6. Or you can do 0, 1, 2, 3, 2, 3, 0, also length 6. And of course, you see that there are cycles of length 8, of length 10, and so on. But these are the only possible cycles. So there's no cycle of length 5, for example, or length 7. So we see here graphically that J0 is the set 4, 6, 8, 10, etc. Now, not all elements in the set J0 are multiples of 4. But the greatest common divisor is 2. They are all multiples of 2. Now, if you consider now 1, there is a cycle of length 2 from 1 to 1, 1 to 1, for example. And there are cycles of length 4, okay, 1, 2, 3, 0, 1, and of length 6 and of length 8. But there are no cycles of odd length, as you may check. So J1, and same thing for 2 and 3. So J1 is 2, 4, 6, 8. Here we see that all states are the even numbers except 0. Okay? But it's not necessarily true that so J0 consists of just multiples. It's not true. So here also we have, it's although J0 is different from J1, but D0 equal D1 equal 2. And we expect that, so all states of this chain have period 2. So we say that the chain is of period 2. Now remark, if it happens that PII is positive, so there is a cycle of length 1 from I to I, then 1, by definition 1, so because PII is PII to the 1, so 1 belongs to JI. And if 1 belongs to the set, then necessarily the greatest common divisor is 1, right? Because DI should divide 1, so it's 1 necessarily. So if it happens that PII is positive, then necessarily I is aperiodic and of period 1. However, the converse is not true. Here's an example. I will not draw the transition, but you can do it easily. Start by doing it. From state 0, we can go to state 1 only. From state 1, we can go back to state 0, and we can still remain in state 1. Okay? Here, P00 is 0. But, as you may check, P00 to the n is positive starting from n equal 2. And there are several ways to see this. Either by the transition graph. So there are cycles of all lengths starting from 2. Okay, so there is a cycle 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, and so on. So you see that there are cycles of all lengths graphically. The second way is to compute the successive powers of p. If you compute p squared, then everything will be positive actually. Try to do it. And therefore, by induction, all powers of p will have positive entries. And P00n is the first entry of Pn, so it's positive. So you can see it algebraically as well. Okay. So here, this is a counterexample. So here actually, this chain is aperiodic, but we don't have P00 is positive. Now, as we expect, all periods in this, all states in the same class have the same period. So if states I and state J communicate, then they have the same period. So how to prove that? Double inequality. But by symmetry, it's enough to prove that di is less or equal than dj. Okay, because the other one follows by symmetry. Or you can say that di divides dj, same thing. Okay, take an arbitrary element in j sub j. Then by definition, pjj to the n is positive. So there is a cycle of length n from j to j. Now, if since j is accessible from I, then there is a path of some length r going from I to j. So pij to the r is positive. And similarly, since I is accessible from j, there is another path from j to I of length m. By a corollary of the Kolmogorov-Chapman equations, pii to the r plus m is bigger or equal than these two, so it's positive. Or if you like, if you can think of it graphically. If there is a path from I to j and a path from j to I, then there's a path from I to I, which is a loop of length r plus m. So, okay. And what does this mean? It means that r plus m belongs to ji. Since di is a divisor of ji, then di divides r plus m. Now again, there is also actually a loop from starting from I of length r plus m plus n. Okay, why is that? Because think of it graphically. I can go from I to j in r steps, and then from j to I, and then go back from I to itself. So I can go from I to j, and from j to itself in n steps, and then from j to I. So if you concatenate or juxtapose all these passes, you get a loop starting from I of length r plus m plus n. So this is another way of seeing this. Okay, so I, j, j, I, j, 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 I. Okay, therefore, r plus m plus n belongs to ji by definition. And since di is a divisor, then di divides r plus m plus n. So di divides r plus m and r plus m plus n. Therefore, it divides the difference, which is n. Now, but n was arbitrary, or an arbitrary element in jj. Therefore, di is a divisor of jj. This is an error here. This is jj. But dj is the biggest divisor. Therefore, di is less or equal than dj. And that's by symmetry, they have the same period. Now, when the chain consists of one class, so we say that the chain is irreducible, all states have a common period, and this common period is called the period of the chain. If the chain is irreducible and has period 1, we say that it's aperiodic. For example, the bonus-malus system that we saw in an earlier video, we see directly that it's aperiodic. It's actually, the matrix, the chain is irreducible because all states communicate. And we had, if you remember, a positive probability of staying at 0. Therefore, the period So 1 belongs to J0, and therefore D0 equal 1, and therefore the period is 1. Now, for the last result, we need two preliminary results, which are interesting. First one is that Ji is stable under addition. What does this mean? It means that if n and m belongs to Ji, then their sum is also in Ji. And once again, this is a consequence of the Kolmogorov-Chapman equation, which we can interpret geometrically. So if n is in Ji, then Pii to the n is positive. And if m is in Ji, then Pii to the m is positive. So Pii to the n plus m is positive. Or if you like, there is a cycle of length m starting from I, and another cycle of length n. If I concatenate the two cycles, I get another cycle of length n plus m. A corollary of this is that Ji is also stable under multiplications by positive numbers. So, otherwise stated, if m and n are in Ji, then any linear combination with positive integer coefficients is also in Ji. The condition that alpha plus beta is positive is necessary because otherwise, if alpha and beta are 0, it's not true, because 0 does not belong to Ji. Okay, so at least one of them should be positive, should be 1 at least. And this is an easy induction, actually. So first I do an induction on beta, and then an induction on alpha. Okay, so take two integers n and m in Ji. The sum is in Ji. So n plus m is in Ji. So n plus m plus 2m is in Ji. So n plus m plus 3m is in Ji. So continuing this process, if you apply lemma 1.2 inductively, we see that n plus beta m is in Ji. Okay, so you can write a reasoning by induction here. Periodicity. And now if I do an induction on alpha, I see that alpha n plus beta m is in Ji. Okay. Therefore, if Ji is not empty, then it's necessarily infinite. Because if it contains one element, yeah. So if it contains two elements, it contains all the linear combinations, so it's infinite. Okay. And now the next result gives an equivalence between two things, two conditions. State di has period 1, and the set Ji contains all the integers starting from a certain rank, which means that starting from a certain rank n, there are cycles of length, of arbitrary length bigger than n, starting from I. So if I start from I can go back to I after capital N steps, after capital N plus 1 steps, after capital N plus 2 steps, and so on. This is the geometric interpretation. Okay, and if this is so, if one of these two holds, so both holds actually, and if state I is accessible from another state J, then there exists an integer capital M starting from which Pjn is positive, which means, once again, that if state I is aperiodic and it's accessible from state J, then there is a path from J to I of arbitrarily sufficiently big length. Okay. Now, 2 implies 1 is easy because if Ji contains two consecutive integers, then the common divisor is 1. So di is 1. It's easy. 1 implies 2 is more tricky. And I will split it into two steps. First of all, Ji is not empty because di is not infinity. And so we claim that Ji contains two consecutive integers, okay, that I would call nu and nu plus 1. So to prove this, we reason by contradiction. If this is not true, then the least difference between any two integers in Ji, call it k, then k is at least bigger or equal than 2, excuse me. Okay? So first thing, if we set k to be the minimum, the smallest difference between any two integers, the first one, of course, being bigger than the second one, or the second one bigger than the first one, then, but since there's no two consecutive integers, k cannot be equal to 1, so it's at least 2. And since it's a minimum, then k is the difference between two integers. So call the first one nu and the second one nu plus k, because they differ by k. And third thing, since it's a minimum, any two difference between two integers is at least k. Okay? Like you can take absolute value, but okay. Now, by assumption, k is not a divisor of j. Why? Because the greatest common divisor is 1. Therefore, there exists an integer n in Ji which is not divisible by k. It's not a multiple of k. So when I do the Euclidean division, when I divide n by k, I get a remainder, which is positive. And now, by the previous corollary, what do we have here? N plus k is in Ji, and nu plus k is in Ji, and nu is in Ji. Okay, so when I do a linear combination of them, so just take take a multiple of nu plus k. Okay, so n2 is in Ji, and n1, which is n plus 1 nu, is also in Ji. So the difference, however, is equal to k minus r, which is less than k. But they should be at least k, so we get a contradiction. So this proves the claim. So there are two consecutive integers, but they not be the one I'm searching for. So I would have to take bigger numbers. So n is not a nu, actually, not necessarily. Okay, so we know that nu and nu plus 1 are in Ji. And now take capital N, which depends on I, to be nu squared. So now my claim is that starting from nu squared, all the integers bigger or equal than nu squared are in Ji. Okay, first thing, we divide n minus nu squared by q. So, by nu. So we get a quotient q and a remainder, which is r, which possibly could be 0, but since it's a remainder, it's less than nu strictly. And now I rewrite n by a trick. So n is nu squared plus q nu plus r, and then I add and subtract r nu. So I can rewrite in this way. Why? Because now this is a positive linear combination of nu plus 1 and nu, and the coefficients, which are r and nu plus q minus r, actually, if I do the sum, I get nu plus q, which is at least 1. So not all of them are 0, right? Therefore, from the corollary, so nu and nu plus 1 are in Ji, so the linear combination of them is in Ji, so n is in Ji. So starting from nu squared, so n was an arbitrary number bigger than n squared. So starting from n squared, all n will be in Ji, and that's it. So the capital N is nu squared. Now I prove the last remark. Suppose that I is accessible from J. So there is an integer m of ij such that pji to the m is positive. And now I use Kolmogorov-Chapman again. So I write pji to the n is bigger than this product, so it's positive. Okay? Provided n is bigger than mij, because I need this to be positive, actually. Okay? If n is big than this number, small m of ij plus capital of ni, which is here, which is nu squared, then this is positive. So there is a path of any length starting from a certain rank, from J to R. And last result, corollary of this, is that if a Markov chain is irreducible and aperiodic, so the period is 1 necessary in this case, then starting from a certain rank, P to the n has positive entries. So all the elements of P to the n are positive for n large enough. Why is that? Because look at this. Here, I and j are arbitrary. Okay, and since the chain is irreducible, I is accessible from any state j. So j and I are so we prove that starting from a certain rank, so take m actually to be the maximum of these mij, because the numbers here actually depend on ij. But if you want something to be independent on I and ij, so the same actually for all states, we have to take the maximum of all these numbers. So it works for all states. And this is a finite number because this chain is finite. Okay. So for n bigger than this number, capital M, pji to the n is positive. But I and j were arbitrary. So all the entries of p to the n, the entries of p to the n are exactly these. Okay. And that's it. So, and we shall use this result in the next video. So this concludes this video, and see you next time.